welcome everyone. I'm Karen Panetta and I'm honored to be the IEEE Awards Board Chair. Today we have the pleasure of being with Dr. Asad Madni, the recipient of IEEE's highest recognition medal, the Medal of Honor, sponsored by the IEEE Foundation. And joining us is also the IEEE Foundation President, Ralph Ford. So first of all, Dr. Madni, congratulations.
Thank you very much, Karen.
And Ralph, if you want to say, talk to Dr. Madni on behalf of the foundation.
I would. Thank you, Karen. Dr. Madni, again, congratulations. And as our viewers know, the Medal of Honor is IEEE's highest honor, and it is not bestowed upon lightly. And your contributions and what you've done, it is significant. We're proud of you, and I'm happy to be here today to be part of this discussion.
Thank you so much to both of you, and I'm extremely grateful for this honor.
So today we're going to talk a little bit about what your inventions are, but more than that, we're going to be talking about how you've developed these technologies, how you've grown them to be so impactful, not just to one domain, but across multiple domains and really change the world. So let's talk about some of your innovations. The first one is the MEMS device that you created for inertial sensors that have saved millions of lives and have spanned every arena, including space exploration, commercial, automotive, and aviation markets. Some of your inventions have had a profound effect in the biomedical fields, one which has improved women's health. So I use the word MEMS, which is a microelectrical mechanical systems device, but most people don't even know what an inertial sensor is. So can we back up and just talk about what the device is and some of the accomplishments that it achieved?
I'd be glad to. So one of the best definitions for MEMS, which the acronym really stands for micro electromechanical systems. I think about 3 decades ago, when there was a real emphasis in our country to commercialize MEMS, the Sandia National Laboratory's Intelligent Micro Machine Initiative had put forward some definitions, and I found them to be very interesting, and I shall repeat them for you. Imagine a machine so small that it is imperceptible to the human eye. Imagine working machines with gears no bigger than a grain of pollen. Imagine these machines being batch fabricated, tens of thousands at a time, at a cost of only a few pennies each. And imagine a realm where the world of design is turned upside down and the seemingly impossible suddenly becomes easy. A place where gravity and inertia are no longer important, but the effects of atomic forces and surface science dominate. So that is the definition. Now, in terms of what is the technology really? MEMS technology creates integrated electromechanical systems that merge computing with sensing and actuation. The mechanical components have dimensions in microns and numbers in millions. Now, when I say dimensions in microns, for the audience, it may be worthwhile for you to consider what the thickness of a human hair is. Typically, a human hair has a thickness of about 80 microns. And here we are talking of mechanical components that have dimensions in a few microns. So that should give you some idea of how small these devices are. They use materials and processes of the semiconductor electronics. And the key characteristics are miniaturization, which is small size and weight, multiplicity, which is batch processing, use of microelectronics, very low cost, and extremely high reliability. So one of the questions that people have asked is, well, if you're using the processes and materials of semiconductor electronics, why did it take MEMS so long to get into production and become ubiquitous? And that's a valid question. So to answer that question, I will say, if you look at the most complex chips that we have today, microelectronics chips, what do they contain? They contain active and passive devices, transistors, diodes, switches, resistors, capacitors, and inductors. And the processes are very well established for them, the deposition, the etching, the masking, and so on. So MEMS uses that. However, the difference is that in addition to these active and passive devices, you have a dynamic device in there. You've got an object that physically is moving, a mechanical component that is physically moving. And interfacing that together with these active and dynamic devices, that's where the real challenge was. The processes had to be really perfected and meet these dimensions and have the repeatability and the producibility and produce them in low cost. So that's what the challenge was. Now, having said that, I'll quote two people just when this whole initiative started. One was Linton Salmon, the director of the National Science Foundation for Solid State and Microstructures. He said, these micro machines have the potential to revolutionize the world the way integrated circuits did. And the other individual, one of the giants in our field, was Ray Stata, chairman and CEO of Analog Devices. He said, micromachining technology has the potential to change the world in some very important ways, many of which are not possible to foresee at this time. In the same way that standard IC technology has so revolutionized our lives and economies. Both these predictions were really prescient visionary statements because they both came true. Today, if you look at the applications of MEMS, they're so wide in commercial, industrial, and aerospace systems. You see them in automobiles, for navigation, for sensing devices, for seat sensors. You see them in aircrafts and drones. You see them in wearable sensors that monitor vital biological signs. Every one of your cell phone has MEMS sensors, which has filters and receivers that are MEMS-based, printers. And that brings us to our discussion today, which is inertial measurement, platform stabilization, personal vehicle navigation, GPS, navigation systems, and so on. So, Dr. Panetta, you asked a question, so what is MEMS and what is inertial sensing? Well, the best way I can describe to you what an inertial sensing is by defining an inertial measurement unit, which is commonly referred to as the IMU. It is a device that measures an object's specific force, the acceleration that's not due to gravity. It also measures angular rate, an object's rate of rotation around an axis, and sometimes orientation in three-dimensional space. It does this by using a combination of accelerometers to get acceleration forces in three axes, X, Y, and Z, and gyroscopes, which are angular rate sensors in three axes, which is roll, pitch, and yaw. And that combined with signals processing circuitry, and in certain cases with magnetometers. So inside an inertial measurement unit are typically three accelerometers, three gyroscopes, and signal processing electronics that detect changes in position and angular rate in three-dimensional space. And these gyroscopes that I talked about, or accelerometers, can be used individually or as part of an inertial measurement unit, depending on the nature of the application. I hope that addresses the question you had asked.
You just brought, Dr. Madni, you just brought science fiction to reality, because most people, when you started out talking about the size of these things and the size of a human hair and how small these things are and they're moving, I immediately think of, the movies where you've got these little tiny robots in your body, and soft body robots are now a real thing. So there's so many new opportunities that are not science fiction because of MEMS. So one of the big things that I noticed is that you've been a champion of utilizing these devices for aviation and the defense industry. But then you had the insight to say, you know what, let's bring this to the commercial market and how it can impact everybody, everyday people. So while all that theory may have been there, so many ideas have been shelved because turning that theory into reality appears to be impossible. And I always say that Dr. Madni is a pioneer for what I call back to the future technologies, where you've looked at theory and said, you know what, that might have not been realizable before, but now it is, and leveraging on new technologies and materials to do that. So let's talk about when you first came up with proposing this. How'd you face getting buy-in from your colleagues? Did they think you were crazy? So I guess I'm asking about your team's reactions when you propose these ideas, especially to go into commercialization after it's been used in the defense industry.
Well, that's a great question, and I'll have to give you some background before I can answer that. But yes, several people thought I was crazy. But remember, one thing we all learned in elementary school and grade school, that necessity is the mother of invention. And this is one of those stories. So let me give you some contextual background. Sister Donner Corporation, where I was for 18 years, eventually as chairman, president, and CEO, had several companies. One of them was the inertial division, where we were making very specialized, high-end, aerospace and defense-based product line of precision accelerometers for space, missile, and aircraft applications. And just before the merger with BEI Technologies that myself and Charles Crocker from the other side led to create BEI Technologies, we had acquired a concept for a Coriolis force tuning fork for angular rate detection. Now, I need to clarify something here. Using a single or dual-ended tuning fork to detect the Coriolis force, which is proportionate to angular rate, was not a new concept. The Sperry Gyrotron company had demonstrated that in the 50s, but it's a massive steel fork. You could take this, hit somebody on the head, and kill them with it. It was that big. But to take that concept and utilize it as the first step towards aerospace and defense, we decided to use monocrystalline piezoelectric quartz. So for those that don't know what that is, it's the same as the quartz crystal in your watch, except that the watch crystal is something where you're detecting the resonant frequency of the crystal, which is relatively easy to do. But here, what you do is, for a dual-ended tuning fork, you vibrate one set of the times, you rotate it about its sensitive axis, which could be X, Y, or Z, roll, pitch, or yaw. And the other set of times will move out of phase, and that is where you detect the signal, which is the Coriolis force that is proportionate to angular rate. So it's much more difficult than just doing what you do in a quartz watch, because here you're detecting a signal, you've got noise, you need signal to noise ratio, and the whole equation for the Coriolis force is based on mass. So you can only compromise mass to a certain extent before you start losing signal to noise ratio. Anyway, so we first started using this and started developing units for the aerospace and defense industry for highly classified projects. I'd like to give you a benchmark because you'll appreciate the challenge as we talk about it. The maximum that we had ever shipped was 10,000 units in a year in single axis, roll, pitch, or yaw, and I one single axis angular rate. And that 10,000 quantity was somewhere between $1,800 to $2,200. We had also produced the world's first MEMS-based inertial measurement unit with 3 accelerometers, 3 gyros, and so on. And those would go into 4- and 5-figure costs. So just to give you an idea. And the reason we say the full MEMS device, because while all the electronics was in an application-specific silicon-based integrated circuit, just our sensor alone was quartz. And there was a reason, because in those days, quartz had much better stability and signal-to-noise ratio than we could get out of silicon. So we had a full ASIC, but the sensing device was in quartz. Okay, so we started shipping these for aerospace and defense, and very soon it went viral. People just started loving us. I mean, they thought this was the best thing since, any other technology that had come in this area. And while we were happy patting ourselves on the back, something happened. The Cold War ended. The Berlin Wall came down. Aerospace and defense business started to take a nosedive. Now, here we were sitting with a technology that nobody else had, a traditional technology. Now, mind you, we had 13 divisions, but I'm talking of this one specific division, the inertial. The business was going down. This new technology could not generate and be the volume to really highly commercialize it. And we were sitting with this thing wondering, what are we going to do? And of course, that made us think that we clearly needed a growth strategy. After performing a very extensive market survey, we identified a significant growth opportunity for an extremely low-cost, solid-state rate gyroscope for automotive stability control brake systems. And since gyroscopes had never been engineered and adaptive to automotive service, the application represented a new, challenging, and emerging market. Now, for those of you that may not know what stability control is and how this is used, this is a single-axis angular rate sensor that detects yaw, which is the lateral movement of the car. It sits somewhere in the middle of the vehicle. The central computer compares this yaw rate with the information it gets from the steering wheel, where we provided optical encoders. And through these optical encoders, you would know how much the steering wheel had turned, how fast it had turned, in what direction it had turned, and through the torque sensor in the same steering column, you would know how much it had turned. So it implied the intent of the driver and the urgency of the driver. The central computer would compare the two, and if at any moment in time, it detected that the car might be behaving in any way other than the intent of the driver, it would take control of the front, left, and rear brakes and apply the appropriate brake to provide a spin out or a rollover. So that's how stability control works. And this becomes very important when you're going through slippery roads, when you're going through gravel or ice. And as a matter of fact, our first customer, General Motors, took me to the track. It was in their Stabilit track system for the Cadillacs and Corvettes, asked me to drive a car on their racetrack. And boy, I couldn't really control it because the spin out was and the potential rollover was a real threat. Well, they turned on this electronic stability control, which had our sensor in it. And really, I mean, my ego was really bolstered of how great a driver I was, when in reality, it was the car that was doing it. So we decided, Charles Crocker, the chairman, and myself, we are going after this business. Now, I want to emphasize something that cannot be overemphasized, is we had no experience in the automotive business. We had grown up in aerospace and defense. We had tremendous amount of successes. And later on in life, I learned that we had actually become victims of our own successes.
How so?
Well, as follows. When the external environment remains relatively stable, and you have done something that has repeatedly granted you success, there is always a tendency to do the same things again. But when the external environment changes and the relevance of your knowledge is no longer applicable, and you try to do things the same way without knowing how to adapt to the external environment, that's a prescription for failure.
Yes.
And there is a reason why I say that. We got the team together and I told them, look, aerospace and defense business is collapsing. because there's no more need to that great an extent because the Berlin Wall has come down.
Mhm.
We're going to go after the automotive industry. Now, I want you to pay very careful attention, I told them. In the automotive industry, there is no loyalty to a vendor like you have in aerospace and defense. If I provide something and somebody can provide it for 1 cent less, unless I can match it, I'm gone. So we are going to have to design these yaw sensors. We call them the QRS, quartz rate sensor, which eventually then became our registered trademark as the gyro chip. So we're going to have to design it, not just to specification, but to cost. The specification levels will be less than what we have accomplished for aerospace and defense, which are very stringent. But the costs are going to be much, much lower. So what does that mean? Well, we're sending a single axis for $1,800, $2,200, and we're going to 4 and 5 figure values for full inertial measurement units. We are going to have to develop these starting at $100 or less. We're going to have to go to $50 and less, and then we're going to have to go to $25 and less. We will have to design this to cost. You cannot use one single extra component or one single extra manufacturing process that will add a penny more to the cost. Now, this didn't sit well with the people. And while they were troubled about this, I said, well, there's one more thing. While we have maximum we've shipped as 10,000 units a year, we're going to have to ship, starting with hundreds of thousands a year. We're going to build it up to 1 million plus a month, and then we're going to have to go to several million a month while we're constantly reducing cost. And then the third thing was something we didn't realize. We thought there was nothing that was more stringent in reliability and quality requirements than aerospace and defense. But boy, we were wrong. We were allowed 1 part per million failure. And if you had 1 part per million failure, we would have the entire customer base coming and haunting us at our facility. So first, we had to redo the whole quality system, enterprise resource planning computer system, electronic data interchange, customer ordering. This was not like aerospace and defense. The customer gives you an order, you enter it. No, they can order 24/7 anytime they want on your system, and you have to be prepared. Your system can't go down because it's going to hold up their entire automotive production. We had to have statistical process controls in place, factory automation in place, technology road mapping techniques for continuous cost reduction, engineering design and validation techniques for lowest unit cost, and the development of a global supplier base so that we can address all the customers worldwide. But the biggest challenge was changing the engineering mentality. And I come back to being victims of our own successes. Several of these engineers had grown up with me, and they're brilliant engineers. Some accepted the fact, others didn't. And I said, look, I'm going to have everyone trained. I will send you people to Switzerland, to the watch companies that will teach you how to handle quartz material and how to grow quartz material. I will bring in the best quality people in the automotive industry to help us revamp and re-engineering our base. I will bring in the best people from manufacturing, but you have to design to cost. Several of the engineers, one in particular, said, we've designed the most complex inertial measurement unit with more components and devices than anybody in the world has. This is going to be below our dignity to do that. I said, well, you can do one of two things. We can certainly apply for the Nobel Prize and we can put your name on it. But as far as the company is concerned, that doesn't help. And the other thing I want to tell you is designing something is not that difficult if you're given enough money.
Mm-hmm.
But designing to cost is a formidable task.
Mm-hmm. Wow.
So this is where we had to go and use inspiration, leadership, technological breakthroughs to reduce the cost and have this thing produced at the lowest cost. Some of the engineers agreed, and I started the training process with the general manager of the division. Some didn't,
Mm-hmm.
and I had to let them go. And these are damn good engineers.
Mhm.
Now, being the president, I was also on the board of the company. And the board of directors said, do you know what you're doing? I mean, you're letting go some of the best engineers. I said, yes, they may be the best engineers, but if they can't contribute to what is needed now, what good is that going to do for the company? This division is fighting for its life right now. And the fact is that just the way an individual outgrows a company can outgrow an individual.
Mhm.
And this is one of those moments. Needless to say, when we were successful, the engineers that left all wanted to come back, and I asked them, give me a good reason why I should take you back. What has changed? So, in addition to automating everything, putting in these quality systems, then we came down to our innovative designs. We use a semiconductor classical technique of, more chips per silicon wafer, right? So we did this on the quartz wafer. And we progressively moved from 1 tuning fork per wafer to 2, 4, 8, 16, 56, and so on. And all these were on the same size wafer. So you'd say, well, what's the big deal? Well, the big deal is this. This is a mass-based device. To detect the Coriolis force is directly a function of the mass of the tines, which is dependent upon the size of the fork. So you reduce that size, you're not going to detect enough signal, you won't get enough signal to noise ratio. And here, we put some of our brilliant people to work. We came up with a design that dramatically reduced the fork size. And in spite of that, we were able to increase the performance by adding additional mass on each of the tines, in spite of making the fork much smaller, and actually increase the mass and increase the signal to noise ratio. To cut a long story short, it happened. We have a lot of scars on our backs, but it was one of the most successful defense conversion stories. And during my tenure, BEI's Systron Down Inertial Division became the world's largest supplier of yaw sensor for cars.
Wow. Wow. What I want to say about that story is there's so much more than just technological innovation. You brought into the whole ecosystem of business strategy, retraining, which is at the heart of all IEEE, that we're all constant life learners, and retooling and not thinking, I'm good enough the way I am. I need to keep moving. I just unbelievable how you pulled it all together and had the insight to know what you didn't know. That's the other thing I really liked.
It took several people. It took several people who I could depend upon, who were innovative, who were willing to take the risk with me. I mean, literally, I had put my job on the line. And just to tell you how dramatic it was, the first year, we were asked to produce 400,000 units. Remember, all we had produced was 10,000 a year. Mm-hmm. While we are doing that, an unusual situation happens in Europe. And this event was the loss of control and rollover of a new European vehicle by a Swedish automobile magazine editor while executing a maneuver to simulate avoidance of an animal such as an elk. It's called an elk test. Well, this car rolled over. Mm-hmm. And the manufacturer committed to equipping all its cars with electronic stability control.
Wow.
And then the CEO of VW, Pish, he said, I want every single car, irrespective. Everyone with stability control. So from there, while we are trying to walk and trying to create these 400,000 units a year, we were told to increase it to 2 million.
That's wonderful.
It was a remarkable thing, but it went on to during my tenure, went on to more than 80 models of passenger cars, and it has saved millions of lives around the world. And then when we created this engine of low cost, high performance sensors, we leveraged it back into the aerospace and defense market, where we brought the cost of aerospace defense market really down, and we captured the entire commercial aviation market. So
unbelievable story.
Commercialization of this technology.
Unbelievable story, and so many lessons for our young people and all of us to learn. Is that it's not just about the technology. But what I want to take away from this is our IEEE Eta Kappa Nu Student Leadership Conference coming up is actually going to be at the NASCAR Hall of Fame. So when we're down there on that racetrack, I'm going to think of you, Dr. Madni.
Thank you.
Watching that.
Thank you.
another one of your amazing accomplishments was, you contributed to the pointing accuracy of the Hubble telescope. So for those of our audience who, don't know why that's so important, I can tell you from doing amateur astronomy, I can't even find the moon. So if you're trying to find something, millions of miles away of a star or something so minute, you really need accuracy. So there's got to be complexity doing things like this, especially in space, to find millions of stars millions of miles away. But again, how did you even connect with NASA? Did you approach them? Did they approach you? How do you even make these connections of the technology to reach out to different fields like that?
Karen, our Precision Systems and Space Division of BI Technologies, located in Maumelle, Arkansas, had a long history and pedigree of creating high-resolution encoders. And believe it or not, their encoder systems were on more than 90% of the spacecrafts that are on orbit today. I mean, as an example, JPSS-1, JPSS-2, GOSAT, GOES, the shuttle remote manipulator system. So it was there on just a tremendous amount. There was tremendous pedigree. It was NASA that approached us. This division actually made electronic organs in the old days when Charles Crocker acquired it. And it was called the Baldwin Piano Company or Baldwin Electronics Company. That's how the BEI name came. And then that technology, they transferred into making patterns on glass discs for incremental and absolute encoders, and became, together with Heidenhain, I think only two companies in the world that could achieve the resolution that was needed, like between 21 to 23 bits of resolution. So NASA had approached us. And to answer your question, well, what is the importance of the thing? You think about it. The Hubble Space Telescope is orbiting the Earth at 18,000 miles per hour. And what it does is it locks on to a bright star, usually known as Cepheid variable, and scans a portion of the sky. And then these optical images are taken. These images are then all put together, and they result in the beautiful images that all of us have seen that has changed our whole understanding of the universe. But think about it, 18,000 miles an hour, you're orbiting. What sort of pointing accuracy do you need? I can give it to you in terms of arc seconds, and I can give it to you in terms of microradian, but I don't think it'll be very useful for some of our audience that are not familiar with that terminology. So let me give it to you in a qualitative way. If you took a US quarter dollar and held it in your hand in Los Angeles, and the Hubble was in San Francisco, it would have to point smack in center of that quarter dollar as it is seen in San Francisco. And because of the Van Allen radiation belts, that beam cannot dither by more than the thickness of that quarter.
Wow.
Okay, so that's the accuracy we had to reach. And we accomplished it by reaching up to 21 to 23 bits of resolution. And with the optical encoder, we had a patented technique called ultralock, which was really a phase lock loop that allowed us to get to such high levels of precision.
Mm-hmm. Wow, amazing, absolutely amazing.
And the same system is there till today. Till today, 32 years since it was launched in 1990.
Mm-hmm.
And it has given us over 1 million, it played a really, really important part in the Hubble giving us over 1 million remarkable images, such as the discovery of Pluto's moons and the formation of galaxies thousands of light years away.
Amazing, absolutely astounding, and renewed new interest in astronomy for young people and our curiosity about our universe. So, Dr. Madni, there's so much that you do that resonates with young people. And one of the things that young people today, they're all socially conscious about their environment and sustainability. But these are values you've had throughout your entire career. As a matter of fact, for our audience, Dr. Madni has numerous honorary degrees from the most prestigious institutions around the globe. And he made history here in Massachusetts when he gave his speech at Tufts University, receiving one of his honorary degrees, because he got a standing ovation. That doesn't happen to engineers, because engineers, right? Nobody thinks about the impact that we make. But it was so clear that you've made such worldwide impact, not just for humanity, not just through leadership, but through every value that you've possessed from the beginning. Can you talk about, the future of design technologies being synergistic with sustainability, and how we can make inroads on these challenges so that young people, they feel committed to continuing these types of technologies and understand the value and that their personal impact can make throughout contributing onto them?
That's a very important question, Dr. Panetta. I believe it's absolutely imperative that we address the environment and sustainability challenges facing humanity. We are all in this together. We also need to appropriately train the next generation of engineers, scientists, and technologists so that they are adequately equipped to address these challenges. And examples of such technologies include the obvious ones, of course: carbon capture and storage systems, more efficient irrigation methods, essential medicines, household water purification devices, and manufacturing processes that minimize waste and pollution. Although it is not a panacea, technology really has the power to increase productivity, efficiency, and cost savings, reduce consumption of non-renewable resources, minimize waste, chemicals, and resources, and measure, analyze, and track progress, all of which can help us minimize the impact on the environment. And in specific terms, we can accomplish this by focusing on certain clean tech applications that are viable, such as public electric transport and electric trucks, cheap and long-term energy storage, plastic recycling, LED light efficiency, the one that I mentioned earlier, carbon capture and storage, alternate energy resources such as solar and wind, of course, fuel cells, smart grid. We need to upgrade our grid, its architecture, sensors, software, middleware, smart buildings. I'm talking about the 4D buildings that actually dynamically move. For example, the Da Vinci Tower that was supposed to have been established in Dubai, but because of the economic collapse in 2008, that was put on hold. But you can see the videos of that if you Google the Da Vinci Tower. Completely sustainable and dynamic moving building. Smart meters, which have actually become ubiquitous now to monitor, compare, and optimize energy consumption. And then bioengineered bacteria, using actual humble soil bacteria in order to create alternatives for gasoline.
Wow.
And I'll give you a very excellent example of technology being used for sustainability. One of the greatest examples is using nanotechnology. Nanotechnology has allowed us to create membranes, as you know, of molecules and with equally spaced holes. We can adjust by manipulating the molecules and atoms, and we can adjust the hole sizes. So if you have these sheets of graphene, which are actually being used now by several states, and think when water molecules with sodium and chlorine ions in salt water encounter a sheet of graphene of this nature with holes of the right size, the water passes through from, say, right to left, but the sodium and chlorine from the salt are blocked. And this is just a wonderful way of desalination and an inexpensive way. So this is one example I'm throwing out at you, but our younger generation will have so many advantages with their sensing techniques and with with the signal processing techniques and with the AI and machine learning techniques to make a really massive impact on sustainability and the impact of climate on our planet.
Wow. And it's interesting because our IEEE Foundation is sponsoring projects all across these fields that you just talked about. So, I think Ralph will resonate with hearing that, because it inspires young people and supports people to do benefit humanity and use their technical skills to impact society. So, it's no question that you are a rock star among the young folks here on every student population, Dr. Madni. And speaking of young people, today's students, they really want to be entrepreneurs. They don't want to start from the bottom. They want to do their own thing. They don't want to work for 20 years for somebody else. They want to jump right in. And I usually encourage and say, do it while you have, while you're used to being poor. So can you talk a little bit or give some advice to young aspiring entrepreneurs? How do they gain business experience? Like you did it and you knew what to do. How do you make that leap to your own venture and explore engaging with future customers?
You asked one of the most important questions, and I think with this Q&A session, the answers to this is probably the most important thing I want to leave behind for our younger generation. This generation does not have the patience that our generation had. Just having a job and being able to put food on the table, was something that I felt I was blessed to have. Today, they want to start their own companies. They're more visionary. They have the resources to be more entrepreneurial. They hear about these great companies being started. But let me tell you something. All this is good, and they should continue that. The backbone of America, the backbone of the United States is our entrepreneurship and innovation. But there are a lot of highly talented and bright entrepreneurs that fail in their business ventures. And this is really a result of not having appropriate business expertise and not doing sufficient homework. I give a seminar that I've conducted all over the world in which there are about 10 or 12 points that I tell people are absolutely imperative if you want to start your own company and you want to commercialize technology. And I hope that our younger audience here is going to pay attention to this. First, what is it? You have to explain the product or service that you're providing in simple, understandable language. Do not assume that the reader or the audience understands your technology, product, or service in as much depth as you do. We engineers have, and I guess, an inherent bias that we think we are very smart because we can use these equations and terminologies, but we forget. You're asking money from and support from individuals that don't understand these words. So you should be catering to them and not the other way around. As an example, my doctoral dissertation was frequency domain reflectometry and digital signal processing solutions to transmission lines and antenna systems analysis. It may sound impressive, but when I'm on Wall Street and seeking financing, how many people do you think really understand that or even give a damn? Now, if I said what I'm presenting to you is an instrument that replaces 9 other instruments that took weeks to perform the measurement with highly trained technicians, this one single instrument can do it in less than 5 minutes with an absolute entry-level technician. Now I think I got their attention. So do that. Second, you have to be very clear. Why are you proposing it? Explain the market you're trying to serve. Just because it was your doctoral dissertation or your master's thesis or whatever is not a sufficient reason. You have to explain why you're proposing it. Which market are you trying to serve? And who else is satisfying this market? If someone is, then you need to explain how you plan to take away their market share. If no one is, then explain how you plan to create and penetrate the market. Here, you need to do a market analysis, which includes market size, key players, and competitive differentiation. And don't just use words what your advisor said or some friend said. Use appropriate, credible references.
Mhm.
Next, you have to be cognizant about intellectual property. No one is going to invest in your company or your product or your service without intellectual property. Explain very clearly what intellectual property you have created and how it is protected. This could be hardware, it could be software or firmware. It could include novel circuits, signal processing, manufacturing processes, etc. If possible, explain how your IP will protect your business from existing or would-be competitors. Then you have to present a proper management team. Show the key players with their relevant backgrounds and related past successes. Remember one thing very important, just because you're the technology guru does not mean you are the appropriate choice for CEO.
Mhm.
Also show management teams financial or in-kind commitment. No one is going to invest without the management team's commitment.
Mhm.
Explain how you plan to have sustained profitable growth. Show clearly how you plan to grow the company. This should include potential customers, their anticipated needs, and your company's ability to service the marketplace with the best price, performance, and quality ratios. Never forget that cash is king and will be integral to both sustaining the early enterprise and financing growth. Nobody's looking for profits in your first 1 or 2 years. They know the mere fact that you're borrowing money, you can't create a profit, but you need to have the cash flow to sustain the enterprise. Be very realistic in your projections. You don't think that just by showing a tremendous amount of growth in an unrealistic period, you're impressing anybody, because you're going to have to live with your own projections. Perform sufficient due diligence before you choose your investors and VCs. Do not get carried away with people who are very eager to invest money and who are looking for short-term returns.
Mhm.
Choose investors who are comfortable with medium to long-range returns and who understand the nature of your business and marketplace. The best investor is someone experienced in your business. Always have an exit strategy. Have a well-defined roadmap in terms of an exit strategy. All investors will want to understand this very clearly. Going public may not be the best solution for everyone. Identify potential buyers for your business before you start it.
Mhm.
Explain why your business fits a buyer. Give investors a reason to invest. In today's economy, there has to be a very compelling reason why investors should risk their money on a startup as opposed to buying shares of excellent companies that are at historic lows.
Mhm.
Do not, as I said earlier, do not become a victim of your past success. Learn to adapt to changing market conditions. Just because an approach made you successful in the past does not mean it will make you successful now, especially if the external environment has changed. Be prepared to work hard and surround yourself with absolutely the best people. And do not be limited by your own imagination. Discuss your plans with a
Mhm.
lot of experienced people. Use a confidential disclosure agreement as appropriate and get feedback. What I want to say is that if you do these things, remember, taking a technology from a laboratory concept to full commercialization is by no means an easy task. The road is long and challenging, but the rewards make it absolutely worthwhile. And if you do these things, then my final recommendations to you is believe in yourself. If you don't believe in yourself, nobody else will.
Mhm.
You will encounter ultra crepidarians in your life. These are individuals who express opinions on matters outside the scope of their knowledge or expertise. Ignore them. Don't operate out of fear of failure. Fear of failure never made anybody creative. And as I said, don't become a victim of your successes. Always keep learning. A learning individual is much more valuable in today's world than a learned individual.
Mhm.
In the past, learned individuals were considered like gods because the external environment had not changed. Today, you want a learning individual. The learned individuals who are not learning will become historians. And I will tell you a very great statement made by one of my favorite authors, Mark Twain. This statement has a deeper truth than one initially realizes. He said, I was educated once. It took me years to get over it. What he's saying is just because you've been educated a certain way, you have to understand it's not valid for all conditions and all times. And remember that knowledge is no longer power. The internet has flattened that curve. What you do with that knowledge is power. And the final thing, be creative and imaginative. As Albert Einstein said, imagination is more important than knowledge. And that's how you will come with innovative and breakthrough ideas.
What an amazing, inspiring, concise list for all of us, not just young people, but all of us that are aspiring to continue to strive to build a better world and better careers. Dr. Madni, you have not only been inspirational in the accomplishments that you've achieved, you do truly walk among the giants, but what's still astounding is that you find time now, even now, to mentor young people, give us all advice. And I see you're wearing proudly your UCLA shirt, which is like the finest institution in the world. And how the final thing is, what is it that drives you to continue to give back when you could just coast and sit back and just relax? What is it?
Well, I genuinely believe that a professional career that has been successful, that does not include philanthropy, is an incomplete and unsatisfying one. I never forget that achieving this privilege in my profession makes it incumbent upon me and my family to give back and help and guide the generation following us, especially the underprivileged. My wife Taj, son Jamal, and I, we actively pursue our philanthropic goals by contributing to various academic, professional, and charitable organizations, including the IEEE, UCLA, National Academy of Engineering, Royal Academy of Engineering, Cal State Northridge, and several others. We've also established several endowed scholarships. And since I retired from my company, I'm serving as a distinguished adjunct professor and distinguished scientist at UCLA, guiding graduate research, mentoring students, inspiring the next generation of engineers, and bringing an awareness of the grand challenges facing humanity to university, community college, and high school students, and I find that very satisfying. But Karen, let me tell you something. It is people like you and others like you that I have encountered that have been inspirational sources and have been the catalyst in terms of the philanthropy I do and what I give specifically to the IEEE. So I just want to tell you, for that and for the inspiration that you have provided, I'm most grateful and I thank you for it.
Oh, thank you so much, Dr. Madni. We couldn't do so much. You've impacted all of IEEE, and the IEEE Foundation is truly grateful for all your continued support.
And I thank Dr. Ralph Ford for spearheading this great foundation and for providing immeasurable resources, inspiration, and guidance to this next generation, the rewards of which we not only see now, but a tremendous amount, unforeseeable rewards we're going to be seeing in the future. So, Dr. Ford, thank you for all that you do.
Dr. Madni, today has just been inspiring. I mean, tremendous amount of wisdom, and we really appreciate the kind words, and just a pleasure to be here today.
Thank you.
And again, congratulations on receiving the IEEE's highest recognition, the Medal of Honor. Thank you all for joining us here today. I hope that you've taken away some great inspirational stories to help impact your own future aspirations and career. On behalf of the IEEE Awards Board, thank you and have a great day. And thank you to Dr. Madni and to Dr. Ford for joining us here today.
Very well. Thank you.
Take care.